Okay, so we are doing this kind of problem that is somewhat voluminous, if you like. So there are multiple steps. The function is complex, and so that's why it's kind of a extended. We get overextended here. So well, let's review first. Okay, so that is the derivative. The function itself is, well, here it is, x squared over x squared minus 1. Okay, so we were able to do pretty much all the job that we care about with nothing but the first derivative, which was simple enough. So that's the graph, and the only thing that we want to make sure that there are no wiggling and the concavity is as we indicated. Okay, so that required differentiation, the second derivative. We found it. The only thing missing is the factoring it, and I'll just factor it for you, so I don't want to do it from scratch. So this is the factoring. 2x minus 1. There are tricks of factoring, obviously, but I just don't want to go there. Okay, so that's it. Okay, all right. So the numerator is factored, and so we just draw the table again. This is pretty much the same table as this one, except, well, we'll see if there are any extra important points. Let's see, and the important points come from factors, but the factors are. These are the factors. The denominator is the same, pretty much. So same factors here as f prime. Okay. Then what else is there? Well, there's actually, let's see, we could cancel it. I didn't realize we could actually cancel x minus 1 once. I don't think it matters. So let's just do it in a manner that is the most straightforward. So list the factors and determine their signs and be done with it. Okay, and then we'll just confirm that that the sign of the second derivative is as indicated, as we know. Okay, so negative 1, hold on a second, negative 1 is whole, and so is 1, okay, and what else? We also had a 0, which is not here, but we do know that it is a whole in the domain, okay. Okay, and then x minus 1 goes to negative up to 1, becomes positive. Okay, x plus 1 negative up to negative 1 then becomes positive. Okay, and the next one, what do we know about the next one? It stays positive, right? Except, well, no, except it's undefined, just as we know that it's undefined at these locations. But otherwise, it does remain positive. And x squared minus 1, or you know that it is positive, then negative here, and then positive. Okay, so we multiply, so f double prime will be positive. Then it becomes, it's still positive. Still positive and positive. Well, actually it is all positive. Who knew? So it is all concave up then. Concave up. That is to be confirms our picture. Wait, one of them is concave down. What did I do wrong here? Hold on a second. X minus 1, x plus 1. let's see, plus 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 minus minus minus, so this one does not contribute anything. X minus 1, x plus 1, it gives me plus minus plus x squared minus 1. Why don't I guess oh, I see. I forgot about, I'm sorry, I forgot about the fourth power, right, over this one. Okay, so these are pluses. Okay, these are pluses, so these in between will be minuses. So concave up, concave down, concave up. Okay, so this is just to confirm. This is just to confirm the picture that we had, and which is this, and indeed concave up, concave down, concave up. Okay, so and then we can say that this is not the case. That does it pretty much. So I'll assign the homework to tonight, and so there will be problems of a little bit of, certainly not of the magnitude of this, but dealing with the first, second derivative, computing first, second derivative. And then once again monotonicity, extreme points, and concavity is what's going to be there for the most part. Okay, so let me start a new one. Okay, so we're still doing derivatives, but we kind of are going to be reversing things in a way, because up until now our the main direction of our analysis was from functions to their derivatives. Okay, so well, derivatives continued. So derivative function, we just did that, its derivative, and then we derived facts about the function, the original function. That's what we did. So sine, for example, as we just did, and here monotonicity. So derivative being positive, negative, and the result is the and then we conclude facts about the function as the function, the original function. Okay, so it is not always the case. Well, once again, we talk about reverse problems, and for the most part, it is the what if we know the derivative or something about the derivative, and we don't know anything about the function. So there are a few things that we could claim. Well, here's a thing that we don't really know. So this is a very simple one. So if f is constant, then so this is the part we are putting aside. Is constant, then f prime is 0. Okay, f is linear, then f prime is a constant. F is quadratic, then f prime is linear, and so on, like that. So these are a few facts that we know about it. What does it mean to reverse? These are facts. These are if-then statements. Okay, and as always with if and statements, what can we do with them? Reverse them, which is called the converse. Converses of all of these statements are valid inquiry for us. So the simplest one is if I take the converse of the first statement, then the f prime is equal to 0. If f prime is equal to 0, then f is constant. So is it true? Or false? Remember that it's not sometimes the converse is true, sometimes it's not. The Fermat's theorem is the last one that did not have the converse, rather the converse is not true, but on the other hand the Pythagorean theorem has its converse is true. So okay, so is it true? The function that is 0, the derivative of which is 0, doesn't mean the function is constant. Yes, it will be yes, and it is kind of that something that you want it to be true, because otherwise it is kind of a strange theory that we're developing here if it was not. So because if once again we go to interpretation of functions as motion, so function is your location, f prime is its velocity, then if your velocity is 0, you shouldn't be moving, right? So velocity is 0. No motion, meaning that you are staying in the same position, so your location is constant. Okay, so that's what you want to do. But the what we have done that should be clearly understood is that we did these statements, these facts that we were looking at are the way we did it. We did not look at the converse. So we took a constant function, we differentiated it, and of course the answer was derivative equal to 0. Reversing it is not necessarily the case, but it can be proven. So so that's another theorem. So f prime is equal to 0, then f is constant, and the answer is, in fact, turns out that the tool that we already have, and that was the purpose of the tool, the mean value theorem is the tool for proving things like that. So well, let's do it. So f prime is equal to 0 certainly implies in there that f is also differentiable. Of course, the missing part here is on an open interval. So, I mean, you don't even have to say that necessarily every time, because differentiability is only defined on an open interval. So you cannot have differentiability of a function that's defined on a single point. So when we say f prime equal to 0 without indicating the point, it means that there is somewhere open interval that on which you have this property satisfied. So at every point of interval I, open interval I, we have derivative first, and secondly it's equal to 0. Okay, so the trick is to use the mean value theorem, and this is how. So take A and B in I, okay, and then compare f of A and f of B. We want to demonstrate that these are the same numbers. Okay, so how do we compare? We subtract f of B minus f of A. Okay, so remember the mean value theorem, it had a fraction, and this was the numerator, what was in the denominator. Let's make B minus A. Okay, I intentionally corrected myself over there to indicate that A is less than B, so that we would not have any trouble with the signs. It actually does matter in this occasion, but in general it will make a difference. So on an interval AB, then the mean value theorem is satisfied. So then on interval, not in the original interval AB, but on the interval AB, we have the conditions of the mean value theorem satisfied. So the function is differentiable and it's continuous, and then the fraction. Remember what the punchline of the mean value theorem? It's not there. So what's the conclusion of the mean value theorem? If you don't remember, what is the meaning of the fraction? Geometrical meaning of the fraction? No, it's not the derivative quite yet. Okay, so what's the meaning of the numerator? Is here. What? It is. Yeah, but so what's the meaning? It is, yes. Of?
The graph.
Not strictly speaking. It is the slope of the secant line.
The slope of the line between A and
Right. So this is the line. So this is the slope of, I don't know, L. So this is L, and this is its slope. So, but so that's the meaning of the fraction, okay. But then the theorem, the mean value theorem, says what exactly? This thing is equal to and then there is the derivative appearing there. Do you see? So this is, I mean, this fraction over here, we know what the meaning is on the right, but as far as the function itself is concerned, it only involves 2 points exactly on the graph. Okay, so that's really, and it is the average rate of change of the function of this interval, it is the slope of the secant line, but we are interested in derivatives. So what does this slope have to do with any derivatives? Yeah, that's right. So you see how do I illustrate it with on my picture? There is I mean, the derivative is the tangent line, right? So the slope of the tangent line. So you see where that point is, where that special point. We slide that line, the red line, we slide it in a vertical direction or parallel in any direction as long as it's parallel, until it touches the graph, so that it becomes a tangent line. So I take that line and like this, shift it without changing the slope. So like this. Okay? So like that. So that's a shift. And the point being that we have found then this important point where the slope of the tangent line is equal to the slope of this line. Okay, so I simply write f prime of c, where c is some point between a and b. So that is the mean value theorem. So we want to compare the values of the functions a and b to arbitrate. The trick here is we are trying to demonstrate the function is constant, which means that we have to compare any two values within this interval of the function, and we pick a and b, just call them a and b. Okay, so and then we, for each of those intervals, a, b, small or large, we apply the mean value theorem, and we discover that there is a point between those 2 points with the derivative equal to this fraction. Okay, so you see what's the next step is? What do we know about the derivative of the function? Now look at this statement of the theorem at the top. What does it say? Right there at the top. this one. So what do we conclude now? Well, f prime equal to 0, what does it mean exactly? Derivative equal to 0. We say that derivative equal to 0 on the whole interval. What does it say about derivative at every point? It's also equal to 0. So at every point the derivative is equal to 0. So that point C that we have not found really. We only know from the theorem that there is such a point somewhere, somehow. We don't know where it is. But it doesn't matter. We know what it is. We know what the derivative at that point is. It has got to be equal to 0. Okay, so this is just by the condition of the theorem, this value is equal to 0. So this is by assumption. Okay, so there, what do we conclude from this? The right-hand side is 0, then left-hand side is 0. So this is also equal to 0, right? And if it is equal to 0, remember that the denominator does not contribute anything. Then the numerator has to be equal to 0. F of b minus f of a is equal to 0, or f of b is equal to f of a. Okay, so as you can see, two arbitrary points were picked. How should I put it? Not picked, but rather we ran. By doing this, we ran through all possible pairs of A, B points in the interval I. Okay, any pair of points can be chosen, and then demonstrated that there is no difference of value between those two points. So there's an interval I here somewhere. Then we pick A and B. Okay, and then what we have demonstrated is this. It's on the value of the function on the same level. So we do it point by point, and then which means that there cannot be variability of the function. Imagine that if there is two values that are different. Well, if they were, then we would assign them, we would name them A and B, go through this proof and demonstrate that it cannot happen. Okay, so that's how it works. We're using the unspecified point C because we know so much about the derivative of the function. The derivative is equal to 0, so well, no matter what that C is, as long as it lies within the interval, the derivative will be equal to 0, and therefore f of b is equal to f of a. So that's how proofs, indirect proofs work, relying on something else. So the conclusion, as you can see, is not only expected, it's natural and predictable and very easy to remember. Velocity is 0, then there is no, you are standing still. Okay. Okay. And so that gives at least one of the ideas about the from these, at least one of them, but actually the other two and whatever follows will fall into our lap very, very quickly, because it is actually what we're talking about here is antiderivative. So it's better just to use the proper language right now. So remember the definition of antiderivative. So if f capital prime of is equal to f, then f capital is called an antiderivative of f lowercase. So that's the definition. Okay, and that's what we are doing here. We're going backwards. We're going backwards from a function to its source. Well, maybe I'll change the. I don't think I like these letters here. Let's say f prime is equal to g. Then f is equal to antiderivative of g. So the point is to actually use the previous theorem we just proven to say something about antiderivatives, all antiderivatives of a function. So unfortunately there are infinitely many. Remember that discussion. So for example, x squared prime is equal to 2x. X squared plus 1 squared. X squared plus 1 prime also is equal to 2x. X squared plus 1 plus 7 prime is equal to 2x. So all of these, x squared plus 1, x squared plus 7 are antiderivatives of 2x. Okay? So do you see more antiderivatives of 2x? Yeah, so give me a few, or all of them if you can. So are there more? So you say more, give me some. X squared plus any constant. Well, let's first verify. So indeed x squared plus c prime is equal to, by the sum rule, simply x squared prime plus c prime, and we have 2x plus 0 is equal to 2x, so it checks out. The question, however, really becomes, is that it? Are there more? Well, once again, go back to motion. Go back to motion. If sometimes the answers look less obvious than when we actually use this metaphor. So suppose x squared is actually our location, and it's in 2x is our velocity then. Once again, so x is time, x squared location, 2x velocity. What we are saying that with this velocity, all of these could be our locations. So these are possible locations. X squared plus c is all our possible locations. So what is the difference here? We pick our function x squared first. Let's just pick it because it's the simplest one. So this is my x squared, y equal x squared, and then y equal x squared plus c are all of those parabolas. Remember pre-calculus, shifting of graphs. Okay, so this is how we shift x squared plus 1, x squared plus 2. It's simply the same parabola plus 1 shifted vertically. Okay. So then you can see what the difference between them, once again, if you think of x as time and y location. The number one is simply what's so special about the first location function.
That's our starting location.
No, I think what you're saying is that it starts at 0. So on the y-axis are our initial locations of all these possible motions. Suppose we know our velocity, and we kind of know where we are, but only in comparison to the initial location. We don't know where we are if we don't know, but otherwise we know how far we progress from the initial location. So the green one is only special only because the initial location starting point at x equals 0 is 0. Okay, so but otherwise there is really no difference in that respect. So then that is the idea of I don't know how convincing it sounds, that once again, if you know your velocity, variable velocity, it's clear that if the velocity is constant, then of course you know how far you have progressed over a period of time. You just multiply velocity by time, right? But what if velocity is variable? Okay, so is it clear that it really, you will know how far you have progressed over time, and so if you know then the initial location, you know where you are. It kind of seems plausible, does it? So it's like you look at your speedometer on and on more and more often, and that way you estimate your location based on your speed. But otherwise, there's really no room seemingly to escape in somehow with this same velocity behave like this, okay, and end up with an entirely different location. So that is the plausibility test of what we're trying to say here, and what we're trying to say here is the answer is no. There are no other. There are no other antiderivatives of the function 2x, just x squared plus c, the end. And we can actually, we are in the position to demonstrate it because how? It's actually uncomplicated. Suppose f is another antiderivative of 2x. Just not another, but any antiderivative of 2x. Okay? It means that f prime of x is equal to 2x. But also x squared prime is equal to 2x. Okay? What I can do here, I could subtract. So f prime of x minus x squared prime is equal to 0. Okay? What can I do on the left? On the right I have 0, that's it. What do I do on the left? The difference of two derivatives. What can we do with them? Remember algebra of derivatives? The difference of derivatives is equal to if it was a sum, if it was not the difference but the sum, what we would do? That's right. It is the sum rule. It is the sum rule. You can call it the difference rule, but it is essentially the sum rule. So I could combine them together into one derivative. So it will be f of x minus x squared prime. Okay. So now let's consider what we've got. Then we have a function, the derivative of which is 0. What's the conclusion? No, this is what it says. The derivative of this function f of x minus x squared is 0. But what do we conclude about this new function? F of x minus x squared, what do we know about it? It's a constant. That's right. This is the theorem, right? Right here, we just proved it that if derivative is equal to 0 of any function, then it is constant. That's exactly what we have discovered. That turns out that the f of x minus x squared derivative is equal to 0, so it's constant. And then we have demonstrated that any antiderivative that we pick will differ from x squared but nothing but a constant. Okay, so yes, indeed. So the conclusion then is that there are no other antiderivatives. Of 2x. Turns out that this same idea applies to any function. Any function. It doesn't have to be 2x. You start with any function and then it works out exactly the same way. So let me state this in the form of a theorem. So suppose f prime of x is equal to g prime of x, then on an open interval. So once again, we don't compare one derivative, one point. We have a whole interval. That's without it, the mean-value theorem won't apply. On the whole interval, the function is differentiable and the derivatives are equal. So in other words, these two functions are identical. Okay, then the conclusion is that f and g differ by a constant. Okay, so either you write f of x is equal to g of x plus c, or something like that. So this is pretty much the formula. So if we have, in other words, if we have one antiderivative, and that's what it is, right? So f and g are antiderivatives. Antiderivatives of that function at the top, say h of x is equal to f prime of x, g prime of x. So we're starting with that function, h prime of x, and then we are looking for its antiderivative. And suppose we have two of them, two antiderivatives of f and g. Okay? So, and then we discover that, well, they differ by a constant. What does it mean? It means that we only need one. We have one, and then we'll find all of them. Okay, so that add a constant, find one, add a constant, you have all antiderivatives. Okay, and it is actually a nice picture. Once again, it doesn't matter what the your function looks like. Say, suppose this is g, then how do I find the rest of them? The rest of the antiderivatives. Well, the formula is there, but if I want to do it graphically, then I remember what I do with this. I just shift, right? So let me try to do that. Oops. No, it doesn't. There was a way to do it. Why doesn't? Okay. Let me go back. No, there's a panning type. No, that's type. I don't need type. So it's here, but okay, so there. Okay, and then I can produce as many of these as I like, as long as they differ but by nothing but a constant. So it is always a vertical shift. And so I can produce as many as I like. The picture, it becomes very nice in the sense that can you see what how these functions are related to each other? Even if you ignore that they're just shifted. What is interesting about it is that number one, they cover the whole plane. So as long, at least when it's defined on the whole x-axis, they will cover the whole plane. So for every point that you pick somewhere a point, you can find a curve passing through it. Okay, firstly, and secondly, they don't intersect. So you kind of a split. It's like a fiber thing, or maybe some kind of a fabric. What I was trying to say, some kind of fabric, and then you even though it is kind of a windy, winding through the fabric, these threads, they certainly they don't intersect. If you probably, most typically, of course, you make it like this, but hypothetically, you can have those threads going up, left, right, and so that's what pretty much what we're seeing here. Okay, so that is what we discover. Another interpretation, once again, of this theorem is so it's like two persons running at the same speed, okay, and it's like they're holding like a rod, so between them. So there is nothing. They are not looking at each other. They are not trying to adjust their behavior. All they know that they have some kind of a plan of how fast they're supposed to run, and change it at any moment of time. And they look at the clock and change faster, slower, and then you can just put a rod between them. Well, let's say maybe it's cars. Yeah, maybe cars. So two cars are, as long as they are being driven at the same exact speed, even though that speed is variable, it's as if it's one car. You can connect them by a piece of metal, and that metal will never bend or never break, because that's what this theorem says. The difference will be constant. Okay, so another way how we could get it is in fact, the derivatives are kind of a, how should I put it, the slopes are given. That's what derivative. If you know the derivative, all you know is the slopes. So for example, if I have my function 2x, okay, so, and I'm looking for its antiderivatives, what I know is every antiderivative will cross the y-axis horizontally. Right, x is equal to 0, 2x is equal to 0. So, right, so there you go. Antiderivatives will have to cross it in this fashion. When I'm at 1, so x equal to 0, 2x is equal to 0, and that gives me horizontal slopes. But x equal to 1, 2x is equal to 2. So then my slopes will look like this. So they will be parallel, but at slope 2, x equal 2, 2x is equal to 4. So I'll have slopes more steep like this. So that's how I can collect data about the derivative. And then what happens then when we actually find that antiderivative? We are finding a curve. You see what kind of curve we're looking for? Yeah? Upward, yeah, but it has to exactly follow those lines. So every time it is here, it has to these lines has to be, one of those lines has got to be always one of its tangent lines. Okay, so that is certainly is a challenging proposition. Okay, so you have an infinitely many little intervals drawn with the same slope in a vertical direction, and then you're supposed to find a curve, kind of negotiate through these to get to the well, just to draw a curve. It's like a I don't know, a flow. I'm thinking, what is it? Where do you say? They test aerodynamics of planes in this tube. What's called? Wind tunnel, right? And so sometimes they simply, what they do, or used to, they would put little flags on the fuselage, and they show you the direction of the wind as it passes around it. Okay, so that's exactly what's happening. So they are seeing these green lines, and they derive in which way the wind goes. Okay, so that's kind of an analogy best I can do right now. Okay, so that is anti-differentiation. Then is not really the ambiguity of anti-differentiation is here because there are infinitely many answers to that question, but they are really not differ a lot from each other. It's almost the same function. One you know all. Okay, so and that gives me I can now create a whole table of integral antiderivatives that we have had for the basic functions that we have. So x squared prime is equal to 2x. Now this is how I rewrite it, the opposite operation of differentiation. So call anti-differentiation or integration. 2x dx is equal to x squared plus c. So that would be a complete way to write it. So once again, I'm indicating that's the same thing. And if you start with x squared plus c, you certainly can arrive back to 2x. But you're not allowed to throw out the rest. So omitting the c is not a mistake that is usually tolerated. So never forget that one. And the reason is because you are throwing out infinitely many answers instead of out of all infinitely many possibilities. You only keep one. So if you forget C, that unfortunately that doesn't work out too well. So and then I have sine x prime is equal to cosine x, and then once again I can write it equivalently. It is pretty much the same statement on the left as on the right. Integral cosine x dx is equal to sine x plus c. Okay? That's the same statement. The only issues might be with their differentiability, but all the functions that we know for the time being are differentiable. So let me do a few more. Ax dx is equal to ax plus c, and say logarithm 1x dx is ln x plus c. This one requires an extra note here, just not really, doesn't really require it, but it applies to all of them. But this one, especially, as well as some others, you have to be careful about what is the domain of these functions you're talking about. The domain has got to be an interval. So this is true on any interval, open interval. Okay, so that caveat applies to all of the functions that we have, but it doesn't matter for the first three. It doesn't matter because the function is defined everywhere. So that interval could be just as well be the whole real line. But this one, 1x, is undefined at 0, so you cannot use it. Well, actually, this for completeness sakes. Okay, so well, there's one more. And that is, from the mean value theorem, in a similar fashion, we can derive a little bit more. Well, let me go all the way back to this theorem. So the function is 0. The derivative is 0, then the function is constant. Okay. Well, let me go here. So f is constant, then derivative is positive. Another thing that we know, we use this sort of in a kind of a way that's not fully justified. Function is increasing, then derivative is positive, and then that's once again if-then statement. The question becomes once again: is it reversible? Is the converse true? So is it really true that if derivative is positive, then the function is increasing? We don't really have that. We have it the other way around. For the time being, we looked at it. That was pretty much that theorem that followed monotonicity theorem. So we would apply the same technique to demonstrate that it is indeed the case. The converse is also true. Okay.